In the stuffy air of the hangar, converted into an office space and permeated with the smell of heated machine oil and cheap tobacco, there was a hum that could not be mistaken for anything else. It was not the roar of aircraft engines or the rumble of artillery cannonades, although the work bustling here was directly related to both. It was the sound of the 1940s, a monotonous, rhythmic, hypnotic crackle of hundreds of mechanical calculators merging into a single symphony of human intellect put into mass production. Women sat behind endless rows of gray metal tables. Their backs were perfectly straight, their gaze fixed on columns of numbers, and their fingers danced with incredible speed across the keys of bulky calculating machines of the Friden, Marchant, and Monroe brands. Here, in the depths of the Langley Aeronautical Laboratory, there was no concept of approximately. Here reigned the dictatorship of absolute precision, where a pilot's life or the outcome of a battle depended on the 8th digit after the decimal point. To understand the scale of what was happening, one must imagine not just an office, but a gigantic data processing plant. In those days, the word computer did not refer to an electronic device with a screen and keyboard. Computer was a position, an entry in a workbook, and next to that entry almost always stood a female name. Male engineers, busy designing fuselages and engines, considered calculations to be rough, routine work, unworthy of the high flight of engineering thought. They sketched out formulas and ideas and then handed them over to the computing pool, a room where mathematics transformed from abstract equations into concrete trajectories. The working day of a living computer began exactly at 8 in the morning, but many came earlier to get a seat by the window. Ventilation in old buildings worked terribly, and by noon the heat became unbearable. The dress code was strict and relentless. Skirts below the knee, blouses with covered shoulders, stockings even in 40-degree heat. Trousers were considered an unacceptable liberty, a challenge to public morality. But beneath this outward primness lay grueling work. The women were divided into specialized groups, each responsible for its narrow sector of flight physics. One group calculated drag, another, lift, a third, pressure distribution over the wing surface. The technical side of this process was incredibly complex and demanded inhuman concentration. Imagine the task: calculating the trajectory of an artillery shell fired over a distance of 20 kilometers. This is not just a parabola from a school physics textbook. In the real world, forces acting on the shell change every millisecond. Air density decreases with altitude, temperature changes, wind blows at different speeds and in different directions at different altitudes, and the Earth's rotation, the Coriolis force, deflects the shell sideways. To account for all of this, the women used a method of numerical integration. They broke the shell's flight into tiny time segments, say 1/10 of a second. The process looked like this. The calculator would take the initial data, muzzle velocity and barrel angle. Then she would calculate where the shell would be in 1/10 of a second, considering the current air resistance. Having obtained new coordinates and a new, slightly decreased velocity, she would move on to the next time segment. And so, step by step, 1,000 steps for a single shot. This was called Euler's method, or more complex variations like the Runge-Kutta method. An error in one line on the third step meant that by the 1,000th step, the result would be absolutely incorrect, and the shell would theoretically fall on its own troops. Therefore, there was a strict verification system. Each problem was solved in parallel by two people, without communicating with each other. At the end of the day, they compared their results. If the numbers matched, the data went to print. If not, both recalculated everything from the very beginning, often staying up long past midnight until their eyes began to water from strain and the numbers started dancing on the paper. The tools these women used deserve a separate description. Their main weapon was a mechanical arithmometer. These were heavy, cast-iron monsters weighing 10 to 15 kilograms. To multiply one multi-digit number by another, one had to enter the digits on the keyboard and then turn a handle or press a button to start an electric motor, which with a terrible screech would turn the gears inside the casing. The noise in the hall was such that one could only talk by raising one's voice. By the end of the shift, many women's hands trembled from the vibration of the keys, and a continuous mechanical ringing filled their ears. Besides the machines, huge paper tables of logarithms and trigonometric functions were used. These books were worn to tatters. The pages with the most popular angles of attack were gray from the graphite of fingers. But the most difficult thing wasn't the noise or the math, but the social atmosphere, permeated by an invisible yet palpable tension. In the era of segregation, especially in the state of Virginia, where the Langley Center was located, laws separated people by skin color even in the Temple of Science. There was a separate group, quote, 0, consisting exclusively of African American women. These women, with brilliant degrees in mathematics, worked in a separate building, in the basement, away from the eyes of the main staff. Their daily life was humiliatingly difficult. To drink coffee, they had to use a separate coffee pot labeled underscore, quote, underscore, 1, underscore. To use the restroom, they had to run across the entire campus to another building, as they were forbidden from using the restrooms in the white-only building. Imagine, you're solving differential equations that determine the success of supersonic flight, but you have to spend 40 minutes of your break just to get to an allowed restroom. In the rain and slush, in heels, knowing that upon your return, your boss will reprimand you for your long absence. It was in this group that women with phenomenal abilities worked, whose names remained in the shadows for a long time. They did the same work as their white colleagues, but often received more complex and inconvenient assignments. For example, analyzing data from the black boxes of crashed planes or processing films from gun cameras. This required not just knowledge of mathematics, but also nerves of steel. Dissecting the scribbles of self-recorders that captured the last seconds of a pilot's and machine's life, they had to abstract themselves from the tragedy and see only functions and graphs. A special chapter in the work of the computers was the wind tunnels. These were gigantic structures where powerful fans created hurricane-force winds, blowing over aircraft models. The noise there was so deafening that even shouting was useless. They communicated with gestures and notes. The women sat in special observation booths with notebooks, taking real-time readings from pressure gauges and scales. The engineer would change the model's angle of attack, the instrument needles would twitch, and the computer had to instantly record a dozen parameters. An error in recording could cost millions of dollars spent on the wind tunnel run. After the experiment, the hardest part began: data cleaning. The raw numbers from the instruments had to be adjusted for temperature in the tunnel, humidity, and turbulence created by the tunnel walls. This involved hundreds of hours of manual matrix multiplication. With the advent of the jet age, the volume of data grew exponentially. Speeds approached the sound barrier and old formulas ceased to work. In the transonic flight zone, the air behaved unpredictably, compressing and creating shock waves. Equations became nonlinear, and their solution required an even finer integration step. Work desks were piled high with blueprints, copies of drawings and graphs. Women worked 12 hours a day, 6 days a week. Personal life took a back seat. Many couldn't keep up with the pace and quit, but the core remained. For them, mathematics was not just a job, but a way to order the chaos of the world, to find logic where others saw only risk and uncertainty. But the real turning point came with the beginning of the space race. When the Soviet Union launched the first satellite, the panic in the corridors of American agencies was palpable. The task changed dramatically. Now, one had to hit not a target on the ground, but a moving point in the void of space, with the launch itself occurring from a rotating planet. The equations of orbital mechanics were an order of magnitude more complex than ballistics. Here, analytical geometry in three-dimensional space came into play. It was necessary to convert spherical coordinates to Cartesian and vice versa, taking into account the attraction not only of the Earth, but also of the Moon and the Sun. It was at this moment that the first electronic monsters, room-sized computers, began to appear in laboratories. IBM machines required a whole retinue of technicians for their maintenance, were cooled by powerful air conditioners, which people did not have, and operated on punch cards. The women calculators met them with caution. It seemed that the era of manual labor was coming to an end. A machine could do in a second what took a person an hour. But very soon it became clear that the electronic brain was just a _1_. It could calculate lightning fast, but it did not understand the physical meaning of the task. If there was an error in the program, the machine obediently produced an absurd result that could doom the mission. Thus began the transformation of the profession. The women who best knew the mathematical inner workings of flight became the first programmers. They didn't just press buttons, they taught machines to think. The programming process in those years was purely physical. One had to punch holes in cardboard cards in a certain order. One program could consist of thousands of such cards stacked in long boxes. If a box fell and the cards scattered, it was a disaster. Restoring order was almost impossible. Women checked the code with their eyes, reading the holes like musical notes, finding errors in the logic of the algorithm before they even entered the machine. The culmination of this symbiosis of man and machine was John Glenn's flight. The astronaut, whose life depended on the precision of atmospheric re-entry, did not trust soulless electronics. In those days, computers often froze due to power surges or overheating vacuum tubes. Glenn knew this. He understood that the computer had provided a trajectory, but he couldn't be sure that no bit of information had flown out during the calculations. And then he uttered his famous phrase, "Let the girl check the numbers." He was referring to Katherine Johnson, a black female mathematician whose reputation as a human computer was impeccable. This was a moment of peak tension. Katherine received a printout from the electronic computer and sat down to recalculate the same equations manually, using her trusty desktop mechanical calculator. She had to process data about gravitational perturbations, atmospheric density at an altitude of 100 kilometers, and the Earth's rotation speed through her brain. A day and a half of continuous work to verify what the machine had produced in minutes. It was a battle of two approaches, analog intuition and digital speed. When Katherine finished and said, "The results match to the last digit," Glenn calmly boarded the capsule. He entrusted his life not to a machine, but to a woman who had verified the machine. However, as often happens in history, triumph became the beginning of decline. With each passing year, computers became more powerful, smaller, and more reliable. Transistors appeared, then integrated circuits. The Fortran language replaced manual wire laying and card punching. The need for large halls filled with people with mechanical calculators began to disappear. Computing pools were disbanded. Some women retrained as software engineers, becoming the elite of the new digital era. Others, unable to adapt to the abstract logic of program code, were forced to retire or seek clerical work. Silence gradually returned to the halls, but it was a different kind of silence. The hum of servers and the soft click of plastic keyboards. The smell of graphite and sweat disappeared, as did the rhythmic clicking of the mechanical hearts of the calculators. But the legacy of these women remained in the foundation of every modern spaceflight. The methods of code verification, the principles of system duplication, the very culture of zero tolerance for errors. All this was born not in silicon chips, but in the minds of tired women who for years sat over endless tables, forgetting about sleep and rest. Today, when we watch footage of rover landings or reusable rocket launches, we see the triumph of technology. But behind the glossy facade of modernity lie the shadows of those who paved this road by hand. Shadows of women in modest dresses who, with slide rules in hand, stormed the heavens. They were the bridge between the age of steam and the age of digital. Their work was invisible, their names often didn't appear in official reports, and their salaries were many times less than men's. But without their painstaking, exhausting, physically demanding labor, humanity might still be lingering at the threshold of space, unable to step over Earth's gravitational well. This historical experience leaves us with an important lesson in the age of artificial intelligence. We are once again on the verge of a paradigm shift, as machines begin to perform work that we considered an exclusively human prerogative: creativity, analysis, decision-making. But the history of __0_ reminds us, a machine is a tool. It can calculate faster, but it cannot feel responsibility. Behind any algorithm, no matter how perfect it may be, there must be a human capable of asking the question, "1. The ability to doubt, re-verify, and take responsibility is what distinguishes us from a calculator, whether it be mechanical or quantum." The final chord of this story resonates not in space museums, but in every smartphone we hold in our hands. The computing power in your pocket is millions of times greater than the total power of the entire Langley computing department. But the software, navigation, signal processing principles, all of this evolved from those very paper tables filled with pencil. The digital revolution didn't emerge from nowhere. It was calculated by hand, step by step, by women who proved that the human mind has no boundaries, gender, or skin color when faced with a great goal.